Right now, you are watching me on some kind of computer. It might be your laptop, or phone, or tablet, or TV, or even in the metaverse. Everything you see and hear in this video is the result of computers sharing vast amounts of information in the form of ones and zeros. Even the world's most powerful supercomputers are built on this binary system of bits. By rapidly switching these tiny on-off switches between 1 and 0, a computer can perform trillions of operations every second and can encode data, graphics, and sound. It's amazing what computers can do just by flipping bits back and forth from one state to the other. But what if that's not enough? What if we take computers and make them quantum? Up until now, we've made computers faster by giving them more memory and more processors. It's like filling a giant warehouse with more and more workers, each of whom can only do one task at a time. At some point, you're limited by the size of the room and by the need to coordinate among the workers. Quantum computing is like tearing down the warehouse and building a new one. In the new quantum warehouse, each worker is a multitasker, capable of not just flipping bits on or off, but holding them in carefully suspended indeterminate states, while coordinating instantaneously with one another. The basic ingredient of a quantum computer is a quantum bit, or qubit. Instead of a tiny switch between 1 and 0, a qubit makes use of the weird loophole of quantum superposition to be both a 1 and a 0 at the same time. Qubits can also be entangled with one another, so that they can work in concert, even while still being in an indeterminate state. What this means in practical terms is that instead of doing each calculation with each bit one at a time, a quantum computer can do exponentially more calculations all at the same time. Imagine that someone goes into an enormous library and hides a secret message on a scrap of paper in just one book. If you wanted to find it the way a classical computer would, you'd check each book by hand and register a yes or no until you found it. Using a quantum computer is like opening every book simultaneously and finding the secret message right away. Scientists around the world are chomping at the qubit to use quantum computers to solve problems in medicine, biology, engineering, mathematics, and of course, theoretical physics. But computing with qubits is not easy. The carefully prepared quantum states are incredibly fragile. Any interaction with the outside world and the superposition collapses, ruining the whole quantum party. Creating programs to run with qubits and wrangling them to actually do the computation requires extreme precision and a deep understanding of the quantum world. The power that quantum computers can wield has the potential to change the world in complicated ways. One of them is through its effect on cryptography, the methods we use to keep private information secure. In many cases, we secure information with a kind of key that can, in principle, be computed using public information. Up until now, we've relied on the fact that actually performing that calculation would take too long. On a conventional computer, we're talking trillions of years, much longer than the current age of the universe. But some estimates suggest that if we could build a perfectly stable quantum computer with enough qubits right now, it might be possible to perform the same calculation in hours or even seconds. So is all data security lost? Not quite. Some of the same quantum principles that make quantum computers so powerful offer new opportunities for cryptography. Since simply observing a quantum state changes it, quantum cryptography can make eavesdropping physically impossible. If someone intercepts your quantum-encoded decryption key en route, their observation of it disturbs the system out of its delicate preparation, and the recipient can immediately tell it's been compromised.
What has gotten me so excited about quantum computing is that as an undergrad, I learned all these abstract concepts, learned about energy levels, quantized energy levels in my classes. But now I get to go to labs, talk with experimentalists, chemists, biologists, understanding their problems and figuring out how can we solve those with quantum computers. Previously, classical computers couldn't do it. And that makes quantum so new. It's not one field, it's a mix of things, it's interdisciplinary and a whole new area of science.
Quantum computing will certainly change the world in many ways, and will present challenges we haven't even begun to imagine. Will this computing revolution be good for humanity, or bring us a host of new, unforeseen problems? If you ask me, both.